Good evening, ladies and gentlemen. I would like to welcome all of you for this interesting session. Thank you for coming and joining with us. Let me start. In the spirit of reconciliation of IESL NSW chapter acknowledges the traditional custodians of the country throughout Australia and their connections to land, sea, and community. We pay our respect to their elders, past, present, and emerging. And I would like to extend our respect to all Aboriginal and Torres Strait Islander people joining this session today. First of all, let me thank Dr. Nihal Vidarna for accepting our chapter's request to deliver this valuable lecture to our members. It is a great privilege for me to introduce Dr. Nihal Vidarna to the audience who are joining this presentation from various locations around the world. Dr. Nihal obtained his bachelor's degree in civil engineering from University of Moratuwa, master's degree in geotechnical engineering from University of Sydney, and doctorate in structural engineering from University of Canterbury, New Zealand, and also MBA in technology management from Dakins University. From 1993 to 1995, he was the recipient of an industrial fellowship awarded by the Japanese Academy of Science to research in concrete technology, geotechnical, and earthquake engineering. He is currently a technical consultant to Arup Asian Operation for heavy civil infrastructure project in the region. Prior to that, he was Arup's Australia and Asian Dam and Seismic Division leader and global leader for water retaining structures. Prior to 2015, he was the senior practitioner with one of the largest Australian consulting companies designing dams. He has always been respected by the team as a leader who finds solutions and work with the team to overcome constraints and challenges and achieve quality outcomes within the budget. In another recent role, he has acted as the SME for major rail, road, and tunnel project located in highly urbanized settings, such as multi-million-dollar Sydney Light Rail, Sydney Light Rail and Parramatta Light Rail project. As the SME, he was able to utilize a holistic approach to manage significant risk to the project and its stakeholders and deliver the project successfully. Now, let us welcome Dr. Nihal Vidarna to deliver his presentation. Thank you so much.
Thanks, Soti, for the generous introduction. I must say at the very beginning, I was not planning to do this at all, but Siti rang me about 2 weeks ago and said, Nihal, please give us a presentation. So when I was thinking about presentations, I thought, as I have done two on the Parakrama Samudra and recently on the seismic risk in Asia, I thought something I would present a little bit unusual, although it is in a dam setting. But having said that, ground anchors are used in any project around the world. I think if I am correct, the Bank of Ceylon basement in Sri Lanka, Colombo, relies on the ground anchors installed in 1978. One of the first application of ground anchors with the ground zone increased by glass fusion. Basically, they send heated glass in the anchor zone. I think that was done by Sublin, German company. So what I'm going to present today is done about 15 years ago, but it is currently still, to the best of my knowledge, it's not my ego, the largest ground anchor installed ever in the world. Now, the project is a Canning Dam upgrade in Western Australia. If you know the orientation, Perth is very close to Sri Lanka. So for me, from Sydney to Perth, it's a 5-hour flight. So the objective of this one is to strengthen a 65-year-old concrete gravity dam. So when they built dam those days, they either underestimate or disregard some of the loading conditions. It's not common to Australia, so don't think Australian engineers did bad dams. It is everywhere in the world. If I am correct, I think in Sri Lanka, similar dams are Laksapana, DSS Senanayaka Samudra in Inginiagala, Wampara, and also the Nalanda Dam in Matale. I might be wrong where Nalanda Dam is. So these are the dams which, if somebody calculated properly using modern risk profiles, probably would not meet dam safety standards expected today. Now this upgrade cost, I hide the numbers on the presentation. Currently, probably at least Australian dollar 400 to 500 million. Design and investigation, probably current we are looking at Australian dollars 50 million, because as it is largest, we are moving into uncharted waters. We couldn't afford to take any risk on the project. So design and investigation involved a lot of review, challenges, and major revisions. Now, size of W and Northern Territory is almost half of the Australian landmass. So it's a big state. I don't know how many times that of Sri Lanka. I know Tasmania is 3 times the landmass of Sri Lanka. So if you look at the map, Tasmania versus half of Australia, you can figure it out. So features of the dam, located approximately 30 feet, 34 kilometers east of Perth, and built between 1933 and 1940. I think very similar time era to the Nalanda Dam in Sri Lanka. Primary water supplied for Perth city, probably about 1 million people. So it's a concrete gravity dam. When I said gravity, probably those who are not familiar with gravity, it means the dam strength and stability all relied on the weight. So it's like, you know, somebody sitting on a chair and it's not glued to the floor. Of course, you've got 4 legs. That's how the stability relies on how you, the weight of the person as well as how the legs are oriented. Now, dam height is about 70 meters. So maximum height is about 70 meters. Dam crest length is 470. So it's not that long crest length. Storage capacity 90 million cubic meters. That's 90 gigaliters. It's, I think, much bigger than even Parakrama Samudra. I don't know how many gallons. Now, the why this upgrade was triggered is it is categorized as an extreme hazard dam. That's it. Nothing can go above extreme. That means consequence and risk are unimaginable, and so the design standard loading conditions are no match to what we designing as, for example, the building. You know, if you want to Sydney Opera House, you know, it's not, the loading conditions here would be at least 10-15 times bigger than that designed for the Sydney Opera House. So this is the dam in plan. So that curve on the up is the water side and down the downstream. So it's got a simple curvature, but it's not an arch dam. It's all relied on the gravity. What's on the left shows the dam shape, and I will show you in another slide. What we have done is drill through the dam upstream, those dotted lines, through the foundation, put a cable and grout it in the foundation, in the rock mass 70 meter deep, and then tension it and lock it at the top. So it's basically, if hopefully 100 years down the track, if something happens, our next generation would blame the designers. They strengthen the dam with elastic bands. You know, that's what is on the right is a spillway. It's typical shape of a spillway. That shape is for the hydraulic efficiency. Why extreme hazard classification? I just thought, there would be non-dam engineers. All these cables are applicable to dams, rails, anything. I just thought give a little bit curiosity. What's the extreme hazard classification mean? For example, if the dam breaks, irrespective of whether factor of safety 30, 40, or whatever it is, we had to assume it can break. That's how the industry works. About 100,000 people will be in the flood wave. The dam break, the water travels, and about 100,000 people would be on that flood wave. The dam water wave will reach the population within 1 hour. So if, for example, at night, if the radio system down, everything down, probably people would not know that they got water until water is up to their roof height. So estimated is probably 20,000 lives would be lost. So it's not single limit that many. Can't take chances. Of course, somebody say, the people will die on the roads in some part of the world, Asia, 65,000 people due to accidents or water quality. But these are single events. But when you look at societal risks, people don't like societal risks. That's how our brains are wired. Potential direct and indirect damage, because when it water travels, it takes everything with it. Probably 2003, they estimated this Australian dollars 23 billion. So in rupees, I don't know, it's probably it's a big number. So if it is extreme hazard dam, these are some of the design criteria we had to meet. It has to pass the probable maximum flood, what is called PMF. PMF doesn't have a number, it's not probabilistic, it's a maximum possible. So it doesn't have a 100 year or 200 years as we designed for urban setting. Approximately it's a 10 million year return period. So you can see when even a road here is designed for 2,500 year return period, some politicians think it is coming in 2,500. It's not, it's a probability it can even come tomorrow. And also it has to resist an earthquake of 50,000 year return period. Now, I did a presentation 3 weeks ago not to rely on low seismicity in Sri Lanka and Asia. The dams in Sri Lanka probably designed for, currently they are designed for 1 in 500. So 500 divided by 50,000 divided by 500 is a big difference. So as I put, what's the normally a return period for seismic design of a building is 475 years return period. And one other law, legislative power, is that during any upgrade, as we have done here, we can't compromise the existing risk profile. So we had to remove people downstream or let them be there, but we can't compromise the dam. So basically when we put these cables, we can't break the dam in half and say, sorry, it's a bad luck, we just gave it a try. It's very similar to that. Probably it's not trial and error like that. I think hot topic in Sri Lanka is organic fertilizers. You can't just play games with people's lives. So that's a law. And post-upgrade, if it has to meet all international and core safety standards. So dam standards are now coming from nuclear power industry because they all are hazard, tsunami, all that in one category. So why the upgrade is needed? It's not only standards, it got a severe reaction. That's what I thought, put this one. And there are a lot of engineers nowadays, they Google when they do a concrete mix design. First thing is they don't even ask the guy sitting next to you. Nowadays, I ask the guys next to you, if he can't give answer, we get a textbook and we read it. Now they Google. So Google give all the concrete mix designs. It's like getting medicines. Even university assignments now can be done from Google. So I thought I'll let you put this one. I had about 100 slides on this presentation, just what it is, because it's happening in Sri Lanka as well. There's a process called alkali aggregate reaction. That means silicon aggregates basically reacts with alkaline cement. And the result is the concrete expands. So when it expands internally, it needs water as well as temperature. So water given is a dam, so its water is there and temperature coming from the heat of from the one is heat of hydration, because a dam of this size will probably take 50 years to cool down, and also the sunshine, the solar radiation. So it expands. When it expands due to internal restraint, because inside the body wants to expand, outside doesn't want to that much, it cracks everywhere. And when they build a dam, they do lift joints. You like building it, they do one layer and roughen it up and do the other one. During the war times, sometimes lift joint will be exposed for about 2 years because they had to go to war and they come back. So lift joint is a very weak layer in any project, in any dam. I was working with the irrigation guys, went on holiday in Sri Lanka. Nalanda Dam is a classic example. It got both AAR and very bad lift joints. So this had the same issues. And also now we increase flood inflow, because earlier when they were built this one, probably they look at the return period of 1,000 years. Now it is at least 10 million. And also seismic inadequacy. Those days, probably these dams were not designed for earthquakes at all. And one other key feature of any dams, probably you can see when people go on open this, they take to concrete dams, a gallery. That's probably the most important part of any design. We go through that gallery or hole in the dam, we have drill holes into the foundation to relieve uplift pressures. When water is full on one side upstream, it builds up through the dam as well as the foundation. We do grout curtain, but design grout curtains only cut the seepage, it's not uplift, because we don't know this. We don't know the real hydrogeology until we build the dam when we fill it. It's a good example is Samanalawa Dam in Sri Lanka. I think it can't, water can't go above certain level. If my memory is sound, I think somebody now through leakage, somebody is trying to run a mini hydro. So, it's nothing wrong with the engineering, but you can't predict these things sometimes until you build it. So you have to have contingency. So the conclusion was the dam doesn't meet factor of safety indices with respect to sliding and overturning. Sliding is just it move horizontally. Overturning, of course, you can see it just topple over. So this is what is a dam. I put a question mark. This is only after 8 years. Wrong concrete, wrong aggregate. Probably they never had the geologists. Probably it's 8 years. I don't know even they had Google those days. But so it's after 8 years. You can see it's all cracked. This is a parapet wall in the dam. So it's common here in Australia, basically Western Australia and South Australia. Now similar issues, I think, as I said, DSN and I heard somebody told me Victoria Dam is expanding and they don't do anything. They just write reports, and they write reports and then somewhere I get an email, Nihal, can you help us? I help with it. And then after the 3 years, I see another email. I now have those things straight away going to my junk mail. This is Sri Lanka DS. I visited this one somewhere in 2013 when I was on holiday. So these are cracks on the intake tower and the spillway block. I think they put a pen or pencil and write a report. So intake tower has cracked extensively, including outlet barrel. I think this one give 24 megawatts to the national grid. So people talk about renewal, but when they always talk about new ones in Asia or other part of, because new one has money, and old ones they just let them die themselves. So and probably concrete dam spillway has unbounded lift joints. So it's just those who on the audience from Sri Lanka. Again, rather than going to the anchor straight away, this is the design loads in a dam. On our left, we got headwater. As I said, we got uplift underneath, then we got tailwater. And on top of that, if there's an earthquake, we got earthquake um, going from left to right. So it's, normally ground anchors even here use for railroads, bridges. They normally done to either stabilize the slope or limit the deformation. These ones we have done probably first in the world is to stabilize a big beast, 70-meter high. So you can see it's a big beast. And we did all the work when the dam was full. And I said, uplift pressures. I have done a lot of retaining walls, even here. That's when lawyer sign walls. First thing I ask is, this uplift, these are retaining walls in the councils and road. And first ask, have you looked at uplift? They say, what uplift you are talking about? We don't have any uplift. I said, groundwater, and we don't have groundwater either, whatever rain. So you look at it carefully. Most things had problems because of the neglect of the uplift. Sadly, most of even the road and other guidelines here never say uplift. And I always said, the standard is not your savior when things go to the lawyers. They expect you to know your duty of care. The standard always has a disclaimer: minimum deemed to satisfy criteria, and it says use your training and experience. That basically say, the standard is very similar to a cookbook. If you cook looking at a cookbook and the meal doesn't go well, I don't think anybody in the world has sued the right of the cookbook. So people had to be very careful when sometimes they become expert, just 3 to 4 years, do the same thing. They say they are expert, and everybody is expert. That will bite you one day. So with this one, when we have problems, we considered few options. One is abandon the existing and build a new one. Probably it's not politically correct. The cost will be very expensive. Concrete buttressing. So it is basically I'll show in the next slide. We built another concrete so that composite action will strengthen the dam. For that to be effective, we had to dewater the storage and then build it. Otherwise, the new buttress doesn't know that they are resisting water. They are just sitting duck. But emptying a storage is not easy. Not only water, you had got flora and fauna. They need to be protected. Other one is install post-tension anchors near the upstream face of the dam. This is the one we selected after multi what called variant estimates. So this is what I called the buttressing. You build another dam or another concrete downstream of the existing dam. This is exactly what they did on the Nalanda Dam in around 2013, I think. Yeah. So that will strengthen the dam, but it needs proper work. It needs dewatering. So this is what we have done. You can see the dam cross section. We drill it through upstream, and they went 70 meters into the rock mass. And you can see what is marked as B is the bonded. We bonded it, and then we tension it. And at the top of the dam, we put an anchor beam and bolt it and left it there. And it can be monitored. Every 5 years, dams need to be monitored. Say they bring a flat jack and see what's the lift off. And then if the load has lost, we re-stress. Now, the current super strands, they are pretty good compared with pre-stressing cables 30, 40 years ago. But still the problem here is if the rock mass loosen up, we want to make sure that the load will be lost and we post tension them. And the reason these have, except that darker one, the bond length, all other free, nothing is connected to this. They are just, it's free, it's not connected to the dam, is that earlier we used to have bonded. With these ones is even if the dam move or rock mass moved under unforeseen condition, the cable will not be fractured. And with this one, we can re-stress it any time and de-stress at any time as well. Once you do grout it, you can't do anything at all. These are super strands, 1300 MPa breaking, and as I will show you later, they got 3 layers of corrosion protection, and probably design life is 150. It didn't bother me 150 or 50 because I don't think I'll be live that long anyway. That's this is 150, but that's the requirement with the bank and the insurance, 150 years. So the bond zone is key to the success, because if it comes off from the bond zone, dam will break in half, because the amount of energy dissipated during the cable de-stressing is enormous. And even stressing, we had to be very careful with safety, because if that breaks, people will get injured. Are ground anchors different? Or you guys may think, oh, this guy is making up a story. We have done this for 50 years. Well, who cares now? There are many names, types. Grouted dowel, you drill a hole, put a bar and grout it, and go home and sleep. Then soil nail, those who work on road projects, if you soil with little cohesion, no strength, we want normal slope is 1:1.5 or 1:2. We can do near vertical, but as excavation process proceeds, we put soil nail and grout them. In the rock bolt, of course, most of the guys who work on hydropower knows rock bolt is geologist thinks is rock bolt is not strength in the rock mass, but just to make sure that it supports the rock mass so that it looks after its own equilibrium. Same principles, but ground anchors are different. They are beast. They carry very large loads. Has a free unbonded length. As I said, through the dam here, it's unbonded, and even some road projects, tunnel projects, we got a free length. As I said, if rock mass moves, we want to make sure it doesn't fracture. They are monitorable here. We can monitor throughout its design life. They are re-stressable. If the load has reduced, we can re-stress them. And of course, if they fail, the failure is explosive because of free length. Now, canning anchor details. This is where probably the presentation starts, but I just want to this one is nothing. You just drill a hole, anchor it, but I just want to give a background, because that is more important than I come and give a sort of largest anchor, and sort of you guys think I inflate my ego. Anyway, I always have an ego. That's another one. Each anchor here, 91 strands, individual cables, individual strands, we got 91. And each strand is 15.2 millimeter equivalent in diameter. And each strand has 7 wires helically twisted. So it's very similar to what you see in bridges, but they are 91. They are massive 91. You can see in another slide, how they are packed. They are manufactured to the top quality in Europe, Switzerland, and I think each wire cable, each strand is X-rayed so that no defects. And here MBL is minimum break-in load is 2,250 tons per cable. So that's our largest capacity to date in the world. Recently, they installed in Tasmania, another state of Australia. I think they were about 85. And so I think somebody told me 225 tons is equal to you lift the USS largest aircraft carrier with the one cable. So it's they are enormous. So the drill diameter was 320 millimeters. So drill from the crest, as I said, it's highly, we don't want to see the drill hole ending up on the storage. So it has to be, I think the accuracy is somewhere on 0.25 degrees. Maximum cable length, 130 meters. So 60 meters into the rock. Hole is only 1 meter away from the water surface, water phase. That's what I said. It's a high risk operation, because if it goes to the storage, you don't want to see the storage coming up in the hole. They at 1.5 meter centers, very closely spaced. They were proof loaded to 75. So we make sure that it is working. We stress it to 78% of the maximum breaking load and lock it off, put the nut and anchor it on the anchor beam at 72% MBL. Rule of thumb is on long term, at least they will have 65% of that load. That's what bridge engineers, when I was at uni 35 to 40 years ago, we learned, so 60%. Now here total of 166 anchors. So each anchor times 130, that is 20 kilometers of anchors. And if we look at strands, each anchor has 7 91 anchors. Each anchor has 7 strands. Strand is 1750 kilometers. I think you can take it around Sri Lanka, one cable. I think still you will get in the cable lift. So it's a big. What are these anchors? High strength super strands. I think the yield strength is somewhere around 1300 MPa. The danger with these ones, they know ductility. Once you go to the yield, they just snap. That's what normally these ones are not used in earthquake design, not in dams, in like bridges and other things. They are not good for earthquakes, where we need ductility. That's what I spoke on the last presentation. Ductility is strength. Is not a good thing in earthquake design. Now these cables have 150 years plus design life. Each strand out of 90, on those 91, each strand is in a greased HDP sheath. So it's like a tube, and it is movable in that sheath. Now all those 91s, and then is contained in another large diameter, 300 millimeter diameter HDP sheath. And both these were, so what then we grout from the bottom bonded zone to the top in one operation. Earlier it done in 2 operations, but here is done in 1 operation. And as I said, I put type G oil well cement. This is the first known use of type G oil well cement, because we did a lot of trials, and Portland cement doesn't have much quality, and they start bleeding. You can see 170 meter deep in one operation. You don't want to see bleeding and segregation. So type G oil well cement is the one oil wells, the cement they use for closing of the oil well. They are expensive. That's the first use, and recently, now I think the Sika produced a very similar one in Australia. Old days, in old dams, they used to be aluminium powder. Nobody knows why it is, but probably get high early age strength. But aluminium in cement is not very good when it comes to sulfate attack. So we find that some of the old cables got problems with Portland cement with aluminium. In the bond length, as I said, what's grouted to the ground in the rock, the outer sheet, that's sheet 300 millimeter diameter, is corrugated, because we want to transfer the bond, otherwise it will come off the rock mass. And all those individual greased sheathing strands have been cut off. So it's bonded that zone. That it is intactness is very important. If it comes off the ground, probably we can say a goodbye to the dam, because it just come off break the dam in half. So typical anchor details, you can see, as I said, at the bottom, see that's the anchor zone, it's anchored there. And then free length is all up to the N or B, it's all free. And at the top, we got a 3 meter deep, at the crest, we build a 3 meter deep anchor beam, and then lock it off. So it's between the deep in the ground, the bond zone, and the top. It's just like a piano wire. So this I got 3 zones. So left to right, it goes from top anchors. But those are the details. I can send this to those who need the presentation. So it's a very, very intricate operation, and the tolerances are just, I don't know even how they got some of those tolerances. It's the contractor was super. So this is the 3 layers of corrosion protection free length. You can see those individual ones got their own HTP sheet, and then they are in to stop them moving in the hole. We got centralizers, and then the larger, darker is the another HTP, smooth HTP, and then centralizer, and then we grout everything except those greased one in individual strands. So one operation. So quality control has to be met 100%. And the grout was done from the bottom, and how they measured it, it's filled with water first, and then they see grout intake versus the water coming out. That needs to be balanced. I would say drilling is rotary percussion drilling, a lot of dust, and we drill each hole. We pressure test them, what is called like with packers, just to make sure it doesn't leak. And if it is leaking, we fill that with grout, and so that grout will permeate into the rock mass, because what we don't want to see is once we do the bond zone concreting, it goes to the rock mass and the grout come out, the cable coming off the ground. And then drill again, wash it, and pressure test again. So it's very expensive. So this is in the bond zone. So that smooth outer HTP became a corrugation, 5 millimeter, and all those individual grease sheet disappeared. So that's the bond transfer zone. We can't have the grease sheet in this one. So one may ask, of course, if you worry about durability that much up, why not here? It's because there's a theory that deep in the rock mass, lack of oxygen will not will inhibit corrosion. Now, as it is, nobody has done before, and most of the textbooks on concrete, where they design anchors, probably little, like thumb-size anchors, and design in lab, but these are unprecedented. So and risks are too high. So as the people were worried even when they stressing. I didn't worry because I have the dual citizenship anyway. I'll be at the airport in the first sound of a cable breaks. Yeah, it's very stressful too. I was the structural supervising structural geotech, but the team was very good. Trial. So we did a trial. How did we trial? We take a big concrete pipe. Same prototype cable. We grouted in the bond zone 12 meters, and we stretched the same and release, and so cut it in half to see what's happening. So why done unprecedented loads? Wanted to see whether corrugated HTP is intact, because if that is intact, probably still there's a corrosion protection. So lost. So we just want to make sure there are myths. Now, if you stretch the cable too much, you break the corrugated HTP, your design is rubbish. These are sometimes myths. People don't do that. As I said, most time they do Google. Even if they write a technical specification for a project, they cut and paste from somebody else. And sometimes the guys don't know these days what they are cutting and pasting. So we just want to make sure it's so commercial contract was able to do the testing. So prototypes, a cable install as like in a dam crest, 3 meter deep beam, loaded to similar, it's very similar to what we would be doing at the site, except the 130 meter long. We just want to make sure the bond length. So this is anchor saw cut after testing. You can see the corrugation is not a good corrugation appearing on the thing. It is intact. That means test. That myth it is debonding, breaking is a lot of myths and garbage. Similar, see the grout has gone between the cables, and that's very important. If one of those has not been grouted, it will come off. So that means the specification project requires you install another, because there's no way it can be repaired. You install another one near to it, nearby. Now this is, I put there's a myth that, the top 4 meters or 2 meters, even little finger size bars here and everywhere, this all coming from a guy in UK wrote Little John, and they use it still as a religious text. Religious text is bad thing because it doesn't give any flexibility, and sometimes people blind faith in the religion it's the same philosophy. You don't test it, you just believe somebody said or somebody wrote, and it's all going in. Even the guy who wrote it doesn't practice it anymore. So it, as you can see, the bond length start at about 6 meters. There is no debonding. It's the load disappeared very quickly. So the load in the bar transferred to the pipe or the dam that's expected in the rock mass very quickly. And that save about 4 meters of each cable. So 4 meter times 166 is a big number in dollars, as long as the unnecessary the excavations. Now these cables are too long, so they made a special trolley. You can see how it is being taken to the side. It's at the dam crest. They had a factory. They bring cables, bare cables, do HDP, grease everything at site, and then bundle them. And this is how it is being taken to the site. So it's still bendable. As a 91 strand is still bendable because it's not 300 millimeter diameter one rod. It's just the cables. They have more flexibility. That's always, cable is better than bars, even in pre-stressed walls and beams. This is how it is being. It has been lowered into the hole. You can see the truss they make, and they all. Somebody will ask, how do you make the vertical? They all have centralizers. That's rollers keeping it in place. Even sometimes I ask road guys, where are your centralizers? It's a couple of dollars. They try to penny pinch, but they don't realize the durability on this one. Durability on a bar. Forget about this one. Even if you install a bar in a rock project, railroad project, the durability for the bar is mainly coming from the alkalinity in the cement. So if we can't get, if you reinforced concrete wall had 75 millimeter cover, close, whatever it is on the standard, and then you forget about your bar, it's got 8 millimeters, it's just out of whack. So you had to make sure that enough cover to the bar in the ground. The alkalinity cement is a must. That's what protects the bar from corrosion. I don't believe in epoxy resins, but just if you can get good cement mix, you had done your job. Now, as I said, it's a heavy load, so we had to transfer that to the dam. So we had to break 3 meters of the dam crest. One reason is dam crest got a lot of alkali aggregate reaction. And when we started breaking, we assumed it's only 32 MPa concrete based on some cylinders, but contractor found it very difficult to break because concrete has matured. So what we had to do is we can't use explosive at the top. Jackhammering or saw cutting is very expensive, not possible. So with this jelly, it's called PFC. I don't know what it stands for. It's a proprietary name. You drill hole and put this gel at night and come back in the morning. Concrete has softened. That's the first use of that. We got it from USA to our knowledge in Australia. Now, put in that. There was a miners got trapped in a gold mine in Tasmania. I think Beaconsfield. They got trapped there for about 2 or 3 weeks, and they didn't want to. The addict they used to rescue those. They didn't want to jackhammer or anything because they didn't want to disturb the rock, and it will probably kill them as well. So they use this material So they drill hole, this put one, next day they come and they can just jackhammer very, very nicely. So it's expensive jelly. Expensive jelly. It's very, as well as very expensive. And the new anchor block will have 550 kilogram of OPC cement. Now, when we look at Perth, some part of some season, Perth, the daytime temperature could be 40 C. At night, it can drop to about 10. So variation is too high. There's a high chance of thermal cracking. On these blocks, we can't have thermal cracking because it has to be one integral unit. What happened is those who know structural engineering, when we put a pre-stress bar, we call spalling. We never talk about bursting steel. Spalling is immediately underneath the anchor, concrete will spall off to the sides. But in high strand, we got bursting as a little bit further, it start bursting. It's at the middle, it try to break in half. So we had to make sure that we don't go and bust the dam in half. Traditional rules is spalling is 4% of the applied. They are okay, but they are based on 30 millimeter, 20 millimeter by meter bar. So we did extensive finite element modeling to make sure that things are not going that bad, or not that bad. It can't go bad anyway. And as I said, it just gave us more confidence that in the rock mass bond, at least we can see ground anchor may come off, but not with the rock, but here it will take the dam with it. Now, this is, I just put the amount of Rio in one of the anchor blocks. As somebody said, if they put a bumblebee inside, it can't find its way out. That much of Rio in it. This is a lot of Rio in it. If a bumblebee can't find its way, you can imagine that's at the dam crest, the amount of steel and the work going on. So these are the thermal stresses. We just make sure that those who involved with heat of hydration, like Syria, what called Syria C660, I think probably it's a British one. I think they use in Sri Lanka. That's currently giving big disasters. Why I say that, can say this, one of some of the references there is work I have done in Japan, but the guys who wrote it didn't know what the references are meant for. So here we did those darker one is a tensile strength grain. It's like young concrete, and then the curves going yo-yo are the thermal stresses. So we would just want to make sure that thermal stresses are below the tensile strength. You can see the temperature is, in this case, hitting about 45 degrees. They had icy water as well. It's a lot of 550 kilogram per cubic meter of cement. I know in Australia there are some bridge beams run into problems. Now, I should mention, if temperature goes too high, we call delayed entrite formation. That's where hydration stops because too hot. And after some time, when water comes, they hydrates and it will break the beam in half. There are bridge capping beams or headstock suffered the same thing because the designer thought they will go for the strength rather than looking at what's the temperature doing. So challenges, managing the risk during design and installation. As I said, it's a high risk, extreme hazard, and to political things and other things, probably societal at risk. 20,000 plus people will probably lose their life. Dealing with the full dam was full. And dust control was a challenge because if your water quality, you had to make sure that dust doesn't go into the storage. In all sides, we stretch the limits. Uncharted territories. Some reviewers, independent reviewers thought it's a little bit crazy, but we had to do it. It's not trying to be the largest in the world or first in the world in like organic fertilizer, just it's a need. So in this one, we'll be monitoring every 5 years. And we want to make sure no loss of processing. As I understand from the client, in 20 years only, loss is about 2%. It's probably less than the accuracy of the measuring device. And I think it won few awards, and also keynote paper at the ICO, that's International Committee on Large Dams Congress in Canada. Then that's the end. Many thanks for listening. Sorry, it's a little bit dam biased, but I thought it would be interesting because anchors are everywhere. Some road designers, soil names, they write 300-page spec for 24mm diameter bar. Still, you look at their test methods, they are copied from somebody else who wrote it about 20 years ago, and guys who wrote it 20 years ago has revised that anyway. So that's the sad part of the thing, and this probably give eye opener to those involved in such projects. I'll stop sharing now. Hi. Hello. What happened? Hello. Hello. Hello.
Hello. Yeah. Sorry.
Yeah, something happened. You guys were quiet. That's what I thought.
Sorry, I went lost a little bit. Okay, sorry.
Yeah, that's okay. So everybody listen the thing, or it got?
No, I got just, I couldn't hear the last 3 minutes, but I'm
Okay.
sure that it's going on. How about others?
I listened to the whole thing. Thank you.
So no
Okay,
need
sure.
to repeat, no?
No, it was all went well until the last. Thank you.
All right. Okay, good. So now I would like to invite the audience to raise any concerns, questions to the presenter. And also there is a few, through the few chats people has asked to the Dr. Nihal, sorry. Yeah. You are putting up a slide, look like, is it DS Senanayaka Samudra? So, and you stated some cracking is evident at Victoria Dam. Can you provide more details? What type of cracks? So
now, okay, Victoria Dam, I haven't heard cracks, but I think it is expanding. That's what, this is alkali aggregate reaction. DSS Senayaka, of course, the intake tower has a lot of cracks. And also the spillway block is leaking. So it's unbonded lift joints. There is no question about it. Even the barrel supplying to the hydropower has cracks in it.
yep,
And people
okay.
know, I think the consultants, I think Indian consultant have found that too. I think they tested in India. It shows that alkali aggregate reaction in the concrete. I put the photo I taken during a visit.
Right, okay. That's
And
good.
of course,
Thank you.
Nalanda Dam, I think Nalanda Dam got alkali aggregate reaction as well. In order to suppress that, I think they put some epoxy layer on the upstream, but it didn't work, as I understand.
I hope that clarifies Mr. Bandala's question. Bandala is the one asked about this one in the chat again. Then there was another question from Dinesh. How was the seating extended / bonded? Any testing or any testing? Heat shrink bonds, yeah.
if that is
heat shrink bonds to crack microsuction, capillary suction with grout. So he has put a question mark there. So, and cyclic loading checks given brittle nature of strands. Okay.
Yeah,
so,
these strands, I said, they have been tested for hydrogen embrittlement. The heat things extensively in Swistel, and these are the it's not like old ones where the hydrogen embrittlement and other things, and with the capillary action, others, even if it happens, it's not a worry because they all are encapsulated in the HTP, double, not even single.
Right. Thanks, Dr. Nihal. Okay. Any further questions from the audience? I got a question. What was the cost to do all these anchors? What was the expected? Did you mention this?
It's
cost,
stability.
Doctor?
It's stability. When we do a wall or anything, we need to make sure that's stable. So with the increased water pressure from the flood, as well as earthquakes, it doesn't have the enough factor of safeties.
Right.
I think Badra replied to the Nalanda Dam, I think, on the chat room.
Yeah, and there's none.
Yeah, there was another one. What was the PGA for the 50,000? It's 0.8 G. I think Dinesh,
Right.
not 0.8 G. So normally for Sri Lanka, the PGA for 500 years is about 0.08 G. So it's 10 times.
May I ask a question, Engineer Gnanasothi? I'm
Yes,
Mrs.
please.
Kamala. Yeah. Dr. Vidana, Nalanda, as you mentioned about the Nalanda Dam, you also got involved. I mean, you were helping us in reviewing the design. And actually, the strengthening was done on the downstream side. So if this type of anchoring was done, what would have been the, you have got a slide with the same type of cross section. So what is your opinion if you used this type of
but the thing, it's nothing to tell bad about Sri Lankan maintenance and operation and maintenance record. Once these anchors are installed, it's very important to monitor them. But as you know, in Sri Lanka, they make the most expensive building, but they don't have a maintenance plan. So that's so. As I said, Nalanda is, I think I changed the design because some designed by some consultants. Probably they came on holiday and took your money and went away. Probably some of the things they done would have destabilized the dam than stabilized. The dam needs to be devoted for buttressing, but if you can do that, buttressing is the best because it doesn't need it's low maintenance done properly. Concrete will last for many years, 70, 80, but cables, once you put the cables, they need to be done properly and they need to be monitored. So that once somebody will do, and after that, it just, that's the worry. Otherwise, cables are clean, environmental wise, no cement, no concrete involved, no foundation preparation. Drill holes and put the cables and go home, but you have to come and check them every 5 years.
Thank you, Neha.
No worries.
So we will allow 1 or 2 questions further. Anything comes up from the audience? look like Dr. Nihal. I think everyone is good with the presentation.
that's
So
good. We are in time
let
anyway.
let me invite our secretary, Dr. Manasi Vijayaratna, to give the vote of thanks on behalf of the IESL New South Wales chapter. Thank you.
Thank you,
Thank
Soti. Good evening,
Yes.
Dr. Nihal Vitarana, ISL NSW Chair, ladies and gentlemen. It's a great honor and privilege to propose the vote of thanks on this occasion on behalf of ISL NSW chapter. Let me first and foremost thank our distinguished presenter, Dr. Nihal Vitarana, for delivering this informative and interesting presentation. We are grateful for the time and effort you took to share your knowledge and experience with us. Secondly, I take this opportunity to thank Engineer Siti Rasin, who took this initiative to coordinate with Dr. Nihal to arrange this event. I would also like to express our sincere thanks to Mr. Chamila Priyantha from IESL headquarters and Engineer Buddhi Vijayaratna from IESL NSW chapter for organizing all the technology-based logistics on the background and making sure this online event runs smoothly. Next, I would like to thank our wonderful audience for your patience and valuable questions. Last but not least, I thank the committee members of our IESL NSW chapter for your cooperation in making this event a resounding success. Looking forward to seeing you all at our next IESL event. Good night and enjoy your evening.
Thank you.
Thank you.